Today we explore how national scientific AI platforms are revolutionizing research by creating shared infrastructure that connects supercomputing, datasets, and automated experiments. These platforms represent a fundamental shift from isolated laboratories to integrated AI-driven ecosystems that accelerate discovery across energy, health, climate, materials, and quantum domains. Let us begin by understanding the transformation from traditional isolated research to connected AI platforms. Traditional research operates in silos, where each laboratory maintains separate computing resources, datasets, and experimental facilities with minimal integration. National AI platforms connect these laboratories through shared supercomputing infrastructure, curated datasets, and automated experimental facilities, creating a network effect for discovery. The United States Genesis mission exemplifies this integration by linking national laboratories, universities, and industry through a unified AI platform. Now let us examine the technical architecture that enables these platforms to function at national scale. The platform architecture consists of 4 integrated layers: scientific foundation models at the top, secure data pipelines below, distributed supercomputing resources, and automated experimental facilities at the base. The platform function emerges from the tensor product of these 4 components working in concert. Scientific foundation models form the cognitive layer of these platforms, learning representations across multiple scientific domains. Foundation models encode scientific data into learned representations that capture underlying physical principles, enabling transfer learning across diverse problems. These models are trained on petabytes of heterogeneous scientific data spanning protein structures, material properties, climate simulations, and quantum chemistry calculations. The model maps input data X through a learned latent representation Z to generate predictions Y that respect physical constraints. An important question: how large are these foundation models in terms of parameters and computational requirements? Current scientific foundation models contain between 100 billion and 1 trillion parameters, comparable to large language models but specialized for scientific reasoning. The platform orchestrates closed-loop cycles that integrate simulation, prediction, and physical experiment in an automated feedback process. The closed loop begins with simulation to generate candidate designs, AI prediction to rank promising options, physical experiments to validate top candidates, and machine learning to update models with new data. The total cycle time is the sum of simulation time, prediction time, experimental time, and learning time for model updates. Traditional research methods require months per iteration due to manual planning, sequential execution, and isolated analysis. National AI platforms compress this to hours or days by parallelizing computation, automating experiments, and continuously updating models. This represents an acceleration factor of 10 to 100 times faster than conventional approaches. Let us quantify how these platforms enable systematic exploration of vast design spaces that were previously intractable. Consider a design space with millions of possible configurations. Traditional methods sample a tiny fraction shown by the colored circles, while AI platforms systematically explore the entire space represented by this grid. Consider battery material optimization, where we must explore composition, structure, and processing conditions. The number of possible designs equals the number of elements to the power of composition sites, times structural configurations, times processing conditions. For 5-element alloys from 50 candidates, 10,000 structures, and 1,000 processing routes, we have 3 quadrillion possible designs. Critical question: can we search 3 quadrillion designs exhaustively with traditional methods? If we test 1 design per week using traditional methods, we would need 60 billion years to complete the search. With AI platforms running 1 million virtual screenings per day through parallel simulation and prediction, we complete the search in just 8 years. These platforms enable unprecedented cross-disciplinary discovery by connecting domains that were previously separate. Energy, climate, health, and quantum research domains converge through shared AI infrastructure that enables transfer learning and cross-pollination of methods. For example, protein folding algorithms developed for drug design are being successfully applied to catalyst discovery for energy applications. Uncertainty quantification methods from climate modeling inform reliability assessments in materials under extreme conditions. Discovery rate scales superlinearly, with the number of connected domains to some power alpha greater than 1 due to network effects. Operating at national scale introduces critical challenges in compute requirements and scale. The compute hierarchy spans exascale supercomputers for foundation model training, petascale systems for simulations, distributed clusters for inference, and edge devices for data collection. Total platform computational power reaches 1 exaflop, or 10 to the 18th floating point operations per second. This computational power requires 20 to 40 megawatts of electrical power, comparable to a small city. Let us estimate the resources needed to train a single scientific foundation model from scratch. Training compute in floating point operations equals approximately 6 times the number of parameters, n times the number of training tokens, d. For 1 trillion parameters and 1 petatoken of data, we need 6 times 10 to the 27 floating point operations. At 1 exaflop, training takes 6 billion seconds, or approximately 200 days of continuous computation. Including hardware amortization and energy costs, a single training run costs $10 to $50 million. Operating at national scale introduces critical challenges in data governance, access control, and security. Data governance must balance open access for public datasets against controlled access for sensitive, proprietary, or security-relevant information. Platforms implement tiered access models with cryptographic authentication and comprehensive audit trails tracking all data usage. Federated learning techniques enable model training on distributed sensitive datasets without centralizing the raw data. Privacy emerges from the combination of differential privacy guarantees, encryption at rest and in transit, and fine-grained access control. AI platforms must address systematic biases and ensure reproducibility of scientific results. Training data bias is illustrated here, where the blue region is densely sampled while the yellow region is underrepresented, leading to models that perform poorly in undersampled domains. Bias enters through non-representative sampling of chemical space, systematic measurement errors in experimental apparatus, and historical focus on certain material classes. Active learning algorithms systematically target undersampled regions to balance the training distribution and reduce bias. Ensuring reproducibility demands rigorous versioning of datasets, model checkpoints, and complete computational workflows. Full reproducibility requires tracking versions of data, models, and code in a cryptographically verifiable lineage. National platforms fundamentally transform collaboration patterns across universities, national laboratories, industry, and government. The platform creates a dense collaboration network connecting universities providing talent and fundamental research, national labs contributing infrastructure, industry offering applications and funding, and government setting strategic priorities. Consider a materials discovery consortium where university researchers propose hypotheses, national lab facilities run experiments, industry validates manufacturing scalability, and government tracks progress toward energy goals. Shared infrastructure dramatically reduces technical and administrative barriers, enabling fluid formation of research teams across institutional boundaries. The number of potential collaborations scales quadratically with participants as the platform enables any-to-any connections. Countries increasingly view scientific AI platforms as strategic infrastructure for national competitiveness. Global investment in national AI platforms shows the United States, European Union, China, and other nations racing to build sovereign infrastructure. Why do nations insist on sovereign AI infrastructure rather than shared global platforms? Key reasons include data sovereignty to control sensitive information, national security concerns about foreign access, and industrial policy to develop domestic AI capabilities. Strategic value derives from innovation leadership, economic competitiveness in AI-driven industries, and security independence from foreign platforms. Leading nations invest billions to tens of billions of dollars in their platforms over 5 to 10-year horizons. Beyond technology, these platforms transform the culture and practice of scientific research. Traditional research follows a linear pipeline from hypothesis to design to experiment to analysis with limited feedback. AI platforms enable continuous cyclic workflows where analysis immediately feeds new hypotheses, creating rapid iterative refinement. The paradigm shifts from purely hypothesis-driven research to discovery-driven exploration, where AI suggests unexpected patterns and relationships. Researchers need new skills, including AI literacy to interpret model predictions, computational thinking to design workflows, and data science to curate training sets. A critical challenge is ensuring that AI-driven discoveries remain interpretable and scientifically rigorous. Foundation models often function as black boxes, producing predictions without clear mechanistic explanations of their reasoning. Explainability techniques include attention visualization, showing which inputs the model focuses on, and feature attribution, quantifying each input contribution to predictions. Physical consistency checks ensure predictions satisfy conservation laws, symmetries, and known bounds even when internal mechanisms are opaque. Scientific trust in AI predictions emerges from high accuracy on benchmarks, physical consistency with known laws, and some level of explainability. National AI platforms will reshape scientific labor markets and career pathways. New career paths will emerge in data curation, AI engineering, and science application domains as platforms transform the way research is conducted and translated into societal impact. National AI platforms will reshape scientific labor markets and career pathways. New career paths will emerge in data curation, AI engineering, and science application domains as platforms transform the way research is conducted and translated into societal impact. In conclusion, national scientific AI platforms have the potential to revolutionize the way we conduct scientific research, accelerating discovery and innovation across various domains.